Welcome to today's paper reading. Today's paper is titled, Lookback Lens, Detecting and Mitigating Contextual Hallucinations in Large Language Models Using Only Attention Maps. This paper was published on the AR14 preprint by Yoon Chuang and colleagues from the Massachusetts Institute of Technology and the University of Washington. In this paper, the authors addressed the issue of contextual hallucinations in large language models, LLMs, where these models generate responses that are inaccurate with respect to the input context. They hypothesized that these hallucinations are related to how much an LLM focuses on the provided context versus its own generated content. Based on this, they propose a simple hallucination detection model called Lookback Lens, which uses the ratio of attention weights on the context versus newly generated tokens. This approach is found to be as effective as more complex detectors. Importantly, the lookback lens can be transferred across different tasks and even models, allowing it to be applied to larger models without retraining. Additionally, the authors demonstrate that this detector can be used to mitigate hallucinations, showing a reduction of 9.6% in the X-sum summarization task through a simple classifier-guided decoding approach. The introduction of this paper highlights a significant issue with large language models, LLMs, which is their tendency to generate hallucinations. Hallucinations refer to content that deviates from factual information or is contextually irrelevant. This presents a major challenge in deploying LLMs effectively. The paper specifically addresses a phenomenon called contextual hallucination, where the model is provided with correct facts but still fails to generate accurate outputs. This issue is particularly prevalent in tasks like summarization and document-based question answering. Most prior studies have focused on scenarios without input context, using LLM representations to detect and mitigate hallucinations. In contrast, this paper emphasizes the importance of the provided contextual information in detecting contextual hallucinations. Figure 1 illustrates the lookback lens, a method for detecting contextual hallucinations in language models. It involves extracting attention weights and calculating lookback ratios for all layers and heads. A linear classifier is trained on these features to predict the truthfulness of the generated text. This approach reduces contextual hallucinations by 9.6% in the X-sum summarization task. To detect contextual hallucinations in large language models, the authors introduce a lookback ratio. This ratio is calculated based on the attention distribution within a transformer model. Specifically, for each head in each layer, the ratio compares the attention weights focused on context tokens versus newly generated tokens. These lookback ratios are then concatenated across all heads and layers to form a feature vector for each time step. This feature vector is averaged over a text span of interest and used as input to a logistic regression classifier, which predicts whether the span is factual or hallucinated. The detection process can utilize either predefined spans, where annotations are available, or a sliding window approach during decoding, which is more practical but more challenging due to potential mixed content within chunks. Table 1 presents the dataset statistics and the evaluation results from GPT-4o on responses generated by Llama 2-7 BChat using greedy decoding. The dataset includes examples from CNN/DM and NQ, with 1,000 and 2,655 examples respectively. The evaluation results show that 49.6% of the responses from CNN/DM and 67.8% from NQ were deemed correct by GPT-4o. Table 2 presents the ORUX scores for classification tasks using predefined span segmentation and a sliding window of size 8 on the NQ, QA, and CNN/DM, SUM, datasets. The source task scores, which are the trained/test scores, are averaged over a twofold validation process. This table highlights the performance metrics of different methods in both predefined span and sliding window settings, as well as their effectiveness in out-of-domain transfer scenarios. Figure 2 illustrates the lookback lens guided decoding process, which involves sampling multiple chunk candidates at each decoding step. The lookback ratios are computed from the attention maps of these candidates, and are then scored by the lookback lens. The candidate with the highest score, indicating it is less likely to be a hallucination, is selected and appended to the generated text. This process is repeated until the end-of-sequence token is generated or the maximum length is reached. To mitigate contextual hallucinations, the authors introduce a classifier-guided decoding strategy. This method incorporates the lookback lens into the decoding process, evaluating multiple token chunks to select the most contextually accurate candidate. The experimental setup includes tasks such as summarization, question answering, and multi-turn conversations, using datasets like XSum, NQ, and MTBench. The results demonstrate significant improvements, particularly in reducing hallucinations by 18.8% on the XSum dataset, showcasing the effectiveness of this approach in maintaining generation quality while minimizing errors. Table 3 presents the decoding results using 8 candidates per chunk in a chunk size of 8. The table compares our methods with greedy decoding and classifier-guided decoding using the NLI models and hidden state representations of different layers. Key results include greedy decoding achieving 49% on XSum and 71.2% on NQ, lookback lens-guided decoding improving to 58.6% on XSum and 74.2% on NQ, and hidden states-based classifier achieving 48.9% on XSum and 73.9% on NQ. These results highlight the effectiveness of lookback lens-guided decoding in improving performance across different tasks. Table 4 presents the results of cross-model transfer on detection tasks. It includes the performance of same-model transfer, 13B13B, and cross-model transfer, 7B13B, across different tasks. The table highlights that while cross-model transfer shows slightly lower results compared to same-model transfer, the OROC scores remain significantly high, indicating the effectiveness of the lookback lens method in transferring detection capabilities across models and tasks. The authors demonstrate the potential of transferring a lookback lens from the Llama 2-7B chat model to the Llama 2-13B chat model without the need for retraining, provided there is a correlation between the attention patterns of the two models. Due to the difference in the number of attention heads between the 7B and 13B models, a linear regression model is employed to map the heads from the 13B model to those in the 7B model. This involves creating matrices of averaged lookback ratios for 1024 heads in the 7B model and 1600 heads in the 13B model. The detection results show that while cross-model transfer yields slightly lower results compared to same-model transfer, the OROC scores remain significantly high. The authors also note that cross-task transfer presents a more challenging setting, which they leave for future work. Table 5 presents the results of cross-model transfer from Llama 2-7B chat to Llama 2-13B chat using two different decoding methods, greedy decoding and classifier-guided sampling, both with a chunk size of 8. The table highlights the performance metrics achieved under these conditions, providing insights into the effectiveness of transferring models and the impact of different decoding strategies. In this section, we explore the effect of varying chunk sizes on the lookback lens-guided decoding. We tested chunk sizes of 4, 8, and 16, finding that while there is a slight preference for shorter chunks in NQ and longer chunks in XSum, improvements are generally consistent across different sizes. Next, we investigate the predictive power of different attention heads. Using all heads versus a subset of the top K heads, we found that while using only the top 10 heads results in worse performance, increasing K to 100 largely recovers the model's performance. Additionally, both positive and negative heads are crucial for generating factual responses. Finally, we experimented with using only a subset of layers for the lookback lens. We observed that predictive power is not concentrated in any specific subset of layers, though middle layers, 13 to 16, 17 to 20, showed slightly higher utility. None of the subsets could fully match the performance of the full model. Table 6 presents a detailed performance comparison across various datasets using different decoding methods and chunk sizes. It highlights the performance of greedy decoding on the NQ and XSum datasets, the improvements observed with lookback lens-guided decoding, and the impact of varying chunk sizes on the effectiveness of these decoding methods. This table is crucial for understanding the optimal conditions for each decoding strategy in different dataset contexts. Table 7 presents the ORAC for cross-task transfer using top K attention heads selected based on coefficients with the largest magnitude, most positive, and most negative values. The analysis considers K values of 10, 50, and 100. The results indicate that while using only the top 10 heads results in lower performance compared to using all heads, increasing K consistently improves performance, with top 100 heads largely recovering the model's performance. Additionally, the study highlights that neither positive nor negative heads alone can match the performance of the top K largest magnitude heads, suggesting the importance of both types of heads for generating factual responses. Table 8 presents the ORAC values for cross-task transfer across various layers. The data indicates that the predictive power is not confined to any specific subset of layers. Notably, the middle layers, specifically layers 13 to 16 and 17 to 20, exhibit slightly higher utility compared to other layers. However, none of the subsets of layers are capable of fully recovering the performance of the model when all layers are utilized. Figure 3 presents a qualitative example from the XSUM dataset, demonstrating the effectiveness of Lookback lens-guided decoding in improving the factual accuracy of summaries generated by the Llama 2-7B chat model. The example contrasts the results of greedy decoding, which produces a hallucination, with the Lookback lens-guided decoding, which assigns low scores to chunk candidates with contextual hallucinations. The predicted scores from the Lookback lens are indicated in the parenthesis, showcasing the model's ability to generate summaries that are faithful to the given context. In the realm of large language models, LLMs, hallucinations are categorized into closed-book and open-book types, with the latter termed as contextual hallucination for clarity. Previous research has predominantly focused on closed-book hallucinations and their detection and mitigation. Unlike these studies, our work concentrates on contextual hallucinations, examining attention maps rather than internal representations. Additionally, we integrate detection into the decoding process for mitigation. Classifier-guided generation techniques, such as PPLM and fudge, aim to control text generation attributes. Our method distinguishes itself by guiding generation using classifiers on attention maps. The self-attention mechanism, initially used in RNN-based models, was pivotal in the transformer model, enhancing parallelization. Our research highlights the effectiveness of attention maps in detecting contextual hallucinations, offering an interpretable solution compared to complex hidden representation methods. The Lookback lens classifier is designed to detect contextual hallucinations by using a lookback ratio computed from attention weights. This classifier not only identifies these hallucinations but also mitigates them through a guided decoding process from the large language model, LLM. The method is versatile, being applicable across various tasks and even across different models by mapping their attention heads. This research introduces new avenues for leveraging attention map information to combat hallucinations in large language models. However, there are limitations to consider. The performance of the Lookback lens is constrained by the LLM's sampling capabilities. If the LLM fails to select the correct chunk from the candidates, the Lookback lens cannot correct the error. Additionally, while the Lookback lens is a lightweight classifier with minimal inference time, the need to sample multiple candidates increases the overall inference time. The method also requires 1,000 to 2,000 annotated examples for training, which is a feasible but notable requirement. Thank you for watching.